And the idea is you're gonna suppose this in memory. And what you do is you bring the first page of R here, then you linear scan through this. And then you bring in the second one, linear scan through this. So by the end of the day, you scan this size n, so this n is m. You scan this n pages m times, one for each page. And by the end of that, you have also scanned this m page once. That's why you need to add this linear cos n. Okay? Yeah, clear for now?
Well, why isn't it built into the m times?
No, it does not, because this only tells you how many times you scan through this. That's the meaning of this. You scan this n pages m times. That's it. But it does not account for the cost of scanning m itself. Okay. Now let's move on. So you saw my announcement in Canvas. I have released the solution to homework 4 and as well as project number 5. And project number 5 is, I guess, the easiest one of all projects you have done. In fact, several of you have contacted me saying that you have finished project 5. That's how easy it is. Okay, so it's like I released it on Sunday, and some of you have finished it by Monday or Tuesday. So I gave you plenty of time as well. You have the due date until December 8th, so you have plenty of time to work on it. And like I said, we will have one more homework based on the transaction and concurrency control stuff we're going to talk about starting from today. And that will wrap up the class. Unfortunately, we lose one lecture on Thursday. Of course, from the instructor point of view, always nice to have one less lecture to teach, but from my perspective, it's a bad news because that means I have one less lecture to cover the things I like to discuss. But we have to live with what we have, so we are losing a lecture on Thanksgiving. That's okay. We'll try to cover as much as I can. I think we can definitely finish all the discussion I want for transaction and concurrency control and crash recovery. It's those additional contents, NoSQL, those things will be affected a little bit. Okay. All right. That's that. That's. Okay, cool. Okay, so why don't we? So today we're going to talk about something completely new, which is different from the discussion we had so far on optimization and evaluation and all that. Okay, and in particular we're going to talk about transactions. So the reason we need to talk about transactions is because of two independent requirements for the database management system. One is concurrent database access, and the other is resilience to system failures. Okay. So a typical use case of database management system is like this. So far in our discussion, we assume that we actually assume two things. One is it's a single user system, meaning that there's only one user that's using the database system, right? If you query or update to the database management system. And the second thing we assume is that the node, the server hosting your database management system never fails. It's always online. You never have to worry about server going down, and things like that. Unfortunately, in real life, both assumptions do not hold. Right? You will have multiple users accessing your data simultaneously, and you will have servers occasionally go offline, right? For whatever reason, right? For whatever reason. So this is a real use case of DBMS in practice. You have your DBMS sitting here, you have software on top, and even more software running on top of that. So there are many application level issues that you need to address in that space, which I covered in the undergrad version of this class that I'm not going to talk about here in the grad level data class. Things like normalization, functional dependency, ER design, data modeling, and how you build a Java program or even web-based program to connect to your database. Those are the things I have covered in the undergrad level data class. That's from those software application layer that we will not discuss in this class. Nevertheless, you can abstract away all those discussions and think about them as multiple users trying to access your database simultaneously. That's the kind of the level of abstraction that you need to have for the discussion we're going to have. Okay. So to give you an example, let's say we have this administration database to Stanford. Okay, and we want to suppose there are two statements we are executing concurrently. The first one says I want to update the enrollment to by another 1,000 students. Okay, and then the second person comes in and says I want to update the enrollment by 1,500. Okay, very simple, right? During the admission seasons, there are two administrators in charge of the admission database of all colleges, and say, okay, for Stanford, I'm gonna upgrade. One guy says, for Stanford, I'm gonna update the admission number by 1,000 additional admissions. The other update by 1,500 admissions. The question is plain and simple. What happened in the end? What's the right value at the end of the day? So in order to understand this, I'm going to introduce a concept called semaphore. How many of you have heard this concept called semaphore? Okay, cool. Some of you have heard of this before. So what is the semaphore? So semaphore, I believe this word originated from the signal control system for running trains. Right? You have train stations. That's just a simple railway, right? The typical scenario for railway is that so there is a switch here that you control the switch so that when the train comes, either the train goes this way, or the train goes this way. Right? You want to make sure when an incoming train goes to the right direction by controlling this switch at the right position. Okay? And there is a sophisticated system of signal control system in place to make sure the train goes to the right track so that there's no cleaner involved. And that system is called semaphore. And in computer science, semaphore was borrowed from this for describing concurrent access to resources. There is some similarity here, right? If you think about this, I call this as my resource. The track or the railway is resource, and the train, you can think about train as your CPU. So these different trains are different CPUs trying to control these resources, and you have to have a way to control them, like who is accessing what at what time. And that's essentially the signal control system for train is, and that's what people call that semaphore. And we're gonna borrow that as the concept that we use to control CPU access to resources, to objects. In particular, Let's look at a very simple example. I call this the museum counter example. Okay? So let's say I have a museum. And this museum has 2 gates. And this is the entry gate, this is the exit gate. Okay? Simple, right? And people come in from here and people exit from here. You cannot get a simpler design than this. Right? That's the simplest design you can have. And suppose you are, given this task by the museum director. He says, okay, why not you implement a simple program? Just the program does one thing, which is to keep track a counter of how many people are currently in my museum. And anytime instance, I can ask your program, send a query to your program, and return me the number of people inside the museum. Very simple, right? If you do that, I give you $1,000. Okay. You think, oh, that's trivial, right? I will design a counter. My program is something like this. Counter C, and this is supposed to be an integer, and then initially 0. Then I just do while loop, right? And inside the while loop, I wait for 2 signals, right? So I wait for signal. And I can, this one and this one, I will put that into 2 threads. So these are threads running in parallel. Okay, so thread 1, thread 2. Okay. So, for example, in C you can use p thread. In other programming language you have different ways of, just initializing multiple threads running in parallel, right? And in each thread, they simply wait for this signal. Whenever you get a signal, you update the counter accordingly. You follow me? Yes or no? And then, of course, you will probably need another thread. This is thread number 3, which is waiting for somebody to send a query to this counter, right? If being queried, I'm going to return this counter, current value of counter. Thread number 3. So this thread they run in parallel or they run concurrently. Okay? You follow me? So what's the problem with this approach? What's wrong with this? First of all, the reason we want to maintain a counter is that the museum has a fair code restriction. Let's say the museum can host only 100 people at most. So whenever it's more than 100 people, it's already 100 people here, I should close this gate. Right? Things like that. Okay, so what's wrong with this approach? What's wrong with this approach? Let's say my current values, so at time t, let's see, at this point, my current counter is okay? And then, at this point, one person show up here, and simultaneously, one person exit from here. Okay? And so both threads will be triggered. The update operation in both threads will be triggered. So at T1, what's going to happen? So let's just say T1 and T2. What's going to happen in this case? Well, we know that if that's the case, the final answer of this should be what? should still be 90. However, there are quite a few different possible answers, right? If you think about it. What are the possible answers you get here? Well, the possible answers, if you run this in concurrent way, the final answer, one possibility is 90, which is the right answer. Another possibility is 89. Another possibility is 91. Why? Why is that? Well, let's look at how we can get this value. Well, this value is trivial. For example, T1 runs to completion, and then T2 starts to run. Or T2 runs, and then this is the, so how do I show this? So this is the one possibility. Let me read this. Another possibility is T2 runs, and then T1 runs. You follow me? So both cases you get this. What about this value? How do you get 89? Well, the idea is T2 average C. So I guess it's easier for me to use this. I'm going to show you the sequence of event, right? Sequence of event. And this is the time dimension. So first of all, is that okay? And then so when you read C, you read into a copy of C prime, right? Because the value of C is in memory, but CPU does not operate on memory directly, so it operates on a copy of that value in cache, in the L2 data cache. So this C prime is a copy of this value C seen by the CPU in L2 cache. So this is the data cache, this is in memory. Okay? You follow me? Yes or no? So you read the value, when you read the value of C, you get a copy of C prime that's equal to 90. And this C prime is you copy in the data cache, operated by thread T2. And then I update this value, which becomes C prime equal to 91. You follow me? What's interesting next is before T2 write this value back to update the value of C, T1 is C. And what's the value of C at this point? It is still 90. It is not 91. You follow me? Because T2 has only updated the copy of C prime in cache, has not pushed the change of C prime back to the original copy of C in memory. So T1, but at this point T1 comes in and reads the value of C. So T1 gets another copy, let's say C double prime, which is 9. Okay? After this, multiple sequence of events is possible. Let's say T2 writes back C, and what happens? The value of C now becomes 91. And finally, so the final value of C equal to 89. Do you follow me? Yeah? How do you get 91? Well, all you need to do is to change this sequence. And then the final value will be 91. Okay? Of course, you can get 90 as well. You don't have to do, I argued just now, if you execute T2 first, then T1, you got 90, meaning that there is no interleaving of actions from the two threads. But even if, a critical observation is, even if you do interleave action from the two threads, it does not necessarily mean you always get the wrong answer. In some scenario, you will still get the correct answer. For example, I may just simply, hold on, let me see. In this case, I don't think it's possible. You have to do them sequentially. In this case, I don't think it's possible. You have to do them sequentially in order to get the right answer. Okay. All right. So that's the problem. So how do you solve this problem? You introduce the concept of semaphore, and you use semaphore to protect the update operation to an object. To make update operation to object atomic. Atomic means that once you use the semaphore to protect, so this will become a semaphore, and this will become a semaphore. And what happens once you use semaphore to protect this is that the update operation to the object C becomes atomic, meaning that if I'm updating the value of C, until the completion of my write the new value back to the C object, nobody else can read the content of this object C. You follow me? What that means is, in this sequence, this event, this particular step, will be blocked and this action can only be executed after which step? After this step, when the update to the object C has completed by the first thread. And that's when I release the semaphore so that you can go ahead. Think about this as two trains trying to run to the same track. You can think about this as, here there is a red light right here, and here is when the red light turns to green light, so that the other train can start moving forward. You follow me? So that's the simple concept of semaphore. That's the simple concept of semaphore. Do all of you follow me? Once we understand that, let's come back here. In this example, we have exactly the same problem as what I have explained here, right? What should be the final value of enrollment? Let's say enrollment initially had the value of 1,000. The correct value at the end of the day should be what? Should be 3,500. But if you don't use something similar to semaphore, you may end up with 2,000 or 2,500 or the correct answer, which is 3,500. You may get one of the three possible outputs. Do you follow me? Yes or no? Okay. So, and this is what I call attribute level inconsistency. And you can also have tuple level inconsistency, right? Suppose I'm updating this application to our department, to the CS department, and the student ID is 123. And I change his or her major to CS, while another person comes in the database and change his or her admission decision to yes. And this is what I call tuple level inconsistency. Why? Because this record, if you think about this record 1, 2, 3, you have some other attribute that I don't really care. Name, address. But then there's a field called decision. Initially it's no. Then there's some other attributes like, I don't know, like age. Then another attribute called major. Initially, let's say to be decided. Then there's some other attributes. Okay? And what's going on is, I call the statement up top called statement 1. I call the statement down below as statement 2. What's wrong with running both of them concurrently? What's wrong with running them concurrently? Well, the first one will make a copy of this, right? Read this record from the database, using B-tree, using heap file scan, whatever. Get a copy of it, read this from disk, and bring to memory, and update this value, right? Update this value in buffer, in the memory, and then read it back to disk. If you don't use something like semaphore to control this process, the first one will change, will keep everything the same. In particular, the decision is still no, while the major changes to CS. That's the first one. The second one will do the same, but change the decision to yes, and the major to keep the same, TBD. Right? No matter which one survives in the end, the final answer is not right. No matter how you look at this, the final answer is not going to be right. Do you follow me? And there is also table level inconsistency. You suppose you update the table using a SQL statement involving a condition. So I set the admission decision to yes for all students with GPA greater than 3.9. Okay, very simple. For students with GPA greater than 3.9, I don't even have to look at their record. I will set the admission decision to yes. And for those lower than 3.9, maybe I will then go ahead, look at their letters, look at their whatever, and then make an informed decision in the end. But the problem with this is that somebody else might be updating the GPA value of those students concurrently. And this is an even bigger problem than this and the first problem we have seen. Why? Because this actually affects the entire table. Let's say you have 1,000 students with GPA, initially with GPA greater than or equal to 3.9. And then another, 2,000 students with GPA that is roughly equal to this. You follow me? In particular, in this range. For all students in this range, do you follow me? For all students in this range, your decision is ambiguous. Because depending on how you are interleaving the actions from those two statements. Some of them, the admission decision will be yes. Some of them, the admission decision will be no. You follow me? For students outside this range, they are actually not affected at all. And for students above this range, they are not affected at all. But only for students in in this range, that's the record that are going to be affected by these two statements. Some of them, emission decision will be no. Some of them, emission decision will be yes, which obviously is wrong, right? Which obviously is wrong. Okay, this is what we call table level inconsistency. And you also have multi-statement inconsistency, right? Even worse, right? For example, while you are doing this, somebody else is doing this, which is to archive the students with a reject decision, right? For emission decision, you could know I'm going to move them from my active database to our archive database because we decided not to omit them. So let's move them from the main database to our archive database. And I'm going to delete them from the applied database as well. While you're doing this, another person is doing the count over these databases. You follow me? And obviously this is not okay. Right? And what should be the count here actually? What should be these two count values? Right? What should be the count value here? You don't know. The answer is you don't know, because if you don't tell me what mechanism you are using to protect the execution of those statements on top, there's no way I can figure out, what's the count of this. You may wonder, what's the big deal if I return some wrong count value here? What's the big deal? Well, for universities, it probably doesn't matter. I mean, this emission people, if I miscount a few students, what's the big deal? But imagine this is Amazon.com, right? I want to count my inventory. I want to count the sales I have. Well, you want to make sure it's right. You want to make sure it's right because customer place order. You want to make sure you actually have the stuff to send to the customer. Or from Amazon.com point of view, when I generate my accounting report, I want to make sure the sales number is accurate. Because if it's not, and you release the accounting report to the public, you will be held accountable, right? If they invest based on this, make wrong decision, they come back and sue you, and you lose millions and millions of dollars. You want to make sure these are right. For university,
Hold on. A couple of books is more important than students.
Well, that's not what I'm saying. I'm just telling quote unquote reality, I guess. Sadly enough, I guess that's probably the case. Okay. All right. So this is the problem number one, which is the concurrent execution of SQL statements. There is a simple solution to this problem, which is to execute them in isolation. Meaning that when there's an active user in the database system, all the other users, you guys have to wait for the first one to finish all his or her jobs in order for you to run anything against the database. And this obviously is the right thing to do. I mean, it's a guaranteed correct output in the end. And all the problems we have discussed so far will go away. For example, in this case, what that means is you don't execute this in parallel, rather you do this, then you do this. Then this, by the time you are doing this, this is already CS. Then everything is right. But efficiency is gonna suffer a lot. I mean, if you do this again on a university database, not a big deal. Right? You tell this admission office people, guys, do this one by one. They are probably pretty happy about it, right? I just wait, surf that a little bit. Hey, are you done? Oh, I can do it. Okay, cool. I do it. But if you tell Amazon to do this, that's not going to work, right? You tell Amazon customer, you guys have to wait. This guy finished purchase, the next one comes in. You're not going to make any money by doing that, right? So in real world, this doesn't work. So this this brings up the concept of transaction. And in most database systems, you can interact with database through this concept called transaction by the following keywords. You do start transaction to indicate that this is the start of my transaction and all the actions following this statement is part of my transaction. What that means is that all those statements following this keyword, start transaction, is supposed to be quote-unquote atomic. Pretty much like the concept of semaphore. It's kind of like you can do this as a simple transaction. So transaction is a collection of statements that's supposed to be atomic. Atomic means that they need to be either all of them get executed or none of them is executed. That's what we mean by atomic. And you signify to the database system you are ready to commit the transaction, meaning that by this time, all changes made by this transaction is supposed to be permanent. It's supposed to be permanent. Even if your database server has crashed or whatever, I don't care. If you allow me to commit, these changes by the statements inside this transaction must be permanently reflected in your database server. That's what commit means. And rollback gives the users the flexibility to undo the changes made by a transaction. Meaning that I start transaction, I made a few statements, but then I realize something is wrong. I don't want to make any change caused by the statements inside this transaction. In that case, you call this statement called rollback. It will undo all the changes you have done so far to the database system by this particular transaction, by the current transaction. You may wonder, okay, what happened to the MySQL or all the other database management systems you've been using, right? Before this class, you probably don't know this concept called transaction. What happened to those statements I have typed? Well, most DBMS has a particular operation mode called auto-commit. And by default, auto-commit is true. Auto-commit is true. And every single statement you type is viewed as a transaction. So effectively, when you type an update statement, when you type a query statement to your database, by default what's going on is it will augment that statement with start transaction and commit once you finish that statement and you execute that statement. You follow me? By default, it's kind of like start transaction, use statement, and commit. Okay? So I'm going to run this simple example to show you the effect of transaction in a real database engine. I'm going to use, again, the class-wide database you have used for your homework 2 or 3, I cannot remember, right? The one that you used to write your SQL statement. So without further ado, let's go to that database. You see? Okay. Okay. So these are databases I have. I'm going to use this. I'm going to use this database. Okay, that's my tables. So for this demo, I need to bring up another. What's the username for your class account? CS, do you still remember? Do you remember this password?
DB at Utah Fall 15.
DB?
db at db at Utah fall 15.
Is that right? DB at Utah 450. And the username is CS65, sorry?
Yes.
Okay. Of course, this user, I do not allow this user to update the database. That's fine. So now I have two users logging to the same database concurrently. Okay. What I'm gonna do is here I'm gonna start transaction. So now I'm inside a transaction. You follow me? I'm inside a transaction. I'm gonna do a few things. First I'm gonna do that. Oh, there is already. So this is, remember, this is the second user, right? This is the second user. And this is the first user. Well, which? I think, yeah, this is the first user. And what I'm going to do here is I'm going to first of all delete this course number 101, the database class from the course table. And then, of course, if I execute the selection statement, you see that record is gone, which is what expected. The user delete the record, you should delete it. What's interesting, we are on the same database, right? The two users are on the same database. Right? What's interesting is to come back and see. This is the second user, right? Second user, do you follow me? What do you see from here? What do you see from here? That record is still there. The record is still there. Do you follow me? Yeah. And so I'm going to insert a new course to this table. Oh, okay. To VNet. Okay. So I insert a new record into this course table. It's called SuperDB. And what do you expect to find? SuperDB. And we come back to the second user here. Well, I still see database. I don't see SuperDB. You follow me? What I'm going to do now is I'm going to tell this guy to meet. Now what do you expect? Oh, you see the change. The second user now sees the change by the first user. Let's do one more experiment. Now the second user, this user cannot, I have to use the first user all the time because the second user, which is your account, is read only. You cannot make any changes to the database. So I'm going to start transaction again. Sorry. Okay? And what I'm going to do is, okay, I'm going to do that, and I'm going to delete from course this record. And And then I'm going to execute the same thing again. Of course, you don't see it anymore, right? And I decide, finally I decide, that's better here. Let's keep this fantastic class. So I'm going to go back. And what happened at that point? It's coming back. And keep in mind, this applies to not only a single statement, but multiple statements. Multiple statements. Finally, by default, if I don't use a transaction, what happens? So once you call rollback or commit, you are outside our transaction. You complete our transaction. If I don't use start transaction, what happens? Well, let's try it out. Okay? You will see the effect immediately. Why? Because auto commit is true. Essentially, this is same as saying start transaction, do this, commit. And let me finish the demo and answer your question. But I can set auto commit to false. What do you expect to happen now? Okay. Then insert into course. I hope this works. Well, also it doesn't work. That's weird. No, when I say auto commit with false, I need to have a commit in order for this to be to show up in the database. Right? But let me try this out. That doesn't work for some reason. But anyway, let me see.
So what does your other user see?
Yeah.
Because it's just in your view. What was the other user
Well, I think even for you view, because if you set auto commit to false, yeah, maybe you're right. Yes, that's right. That's a good point. That's an excellent point, actually. Well, you see this, so I don't know why. So let me try again. Not auto commit to false. Let me try inserting one more record. It still shows. Well, this time it doesn't see this. Okay? You see that? And if I come back, now if I commit, the point is, for the same user session, of course, you expect to see the change, right? But it's important for the other user not to see the change when you set auto commit to false, and meaning that the other user only see the change when you actually commit. So this, okay? Now, if I come back and do auto commit to true. Okay? Here, I will see this record immediately, not surprising. You follow me? But keep in mind, I never type commit statement. But auto commit is true. If things go expected, we see that show up here. Okay? So that's essentially point number one, concurrency control, right? Let's come back to the class, to the slides. One thing you want to make sure in MySQL, go ahead.
Yeah, so the rollback will only work before commit, after commit. Can we make a transaction?
Well, once you commit, you cannot roll back. So you either commit or roll back. Sometimes some database systems don't call that rollback. Some database systems call that abort, which is a more common name, but it's the same thing.
So for the first user,
Louder? Can you speak louder?
for the first user, is it cache? Like why we can see the effect of the?
Well, the first for the that makes sense, right? If you are in one user session, you have to make sure the user see the changes he or she has made so far, because otherwise it's kind of weird, right? I type something, even though I haven't committed yet, but I am updating the status of your database, so I should see the change immediately, even if I haven't committed yet. It's just that the significance of commit is that you are pushing those changes permanently back to the database so that the other users now become aware of this. Okay? It might appear tricky a little bit, but later on when we go on and discuss the property of transaction become clear. So you can wait just for a few more slides and we will discuss this in further details. Yeah.
Where are those changes stored?
Those changes are typically stored by a combination of log, which we haven't discussed yet, but we will discuss that in today's lecture or hopefully in next lecture, and in the buffer. Okay, a combination of that. We will talk about that later on. Okay. By the way, if you are using MySQL database system and some other database systems, by default, the support for transaction is not a by default setting. For example, the default storage engine in MySQL is my ISAM, right? It's my ISAM. But now you should know what ISAM means, right? We talk about that, right? And default storage engine is this, which actually does not support transaction. If you want to support transaction, you have to use a storage engine called InnoDB. And you can change the storage engine of MySQL by using a simple command like this. Or you can check the storage engine of a table by show create table statement, which is it shows you the engine in InnoDB. Means that this table supports transaction.
Why wouldn't it be InnoDB by default?
Well, because supporting transaction means that you have that much overhead.
Just more costly.
More costly. The storage engine become more costly, more overhead. If you are mostly read-only operations and you have a very few update operations, in that case, MySQL, of course, is much more efficient. But if you are update heavy and you have a lot of transactions going on, you want to use InnoDB. Okay, so that's part number one for transaction. Another reason we want to have transaction is the following. We want to be resilient to system failures. So suppose you are doing some bark load operation or some bark insertion or bark update operation. For example, you're doing this. Okay? And in the middle of it, system crash. Power failure, whatever reason, right? And what do you expect? Well, some students got deleted from apply, some have not. And you don't know who has been moved to the archive database and who has been deleted from the apply database. You just don't know because you're in the middle of executing this. And the progress you can make depends on a lot of factors, like what other processes are running currently in the system, what is the current network speed, and so on and so forth. And the point is, when database is back online, when power is resupplied or whatever, you want to resume from where you have stopped, where you have been interrupted. You don't want to, the ideal situation is start right at the time you have been interrupted and go from there, so that you don't have to waste any effort you have done, and you have to redo anything that you have already done. So that is the point of resilience to system failures. And how can transaction help this? Okay, so this is the example I just gave you, right? So you are moving data from one table to another table. In the middle of it, system crash. You don't know how much data has been moved over, how much data has been deleted, and so on and so forth. Another reason for having resilience to system failure important for database is to come back to, which is related to the question he just asked, where those changes are kept. If you recall the project 2 we have done, we asked you to do buffer manager, right? We asked you to do buffer manager, which actually play a critical role in all subsequent projects, right? In Vivek, in sorting, in all of this, right? One thing you should keep in mind is the updates, the change you have made in a database management system. They are not directly pushed back to the disk. Rather, the change and updates you have made are to the copy of the page that's in the buffer. So there are two things going on, right? One is this is your disk. Okay? And this is your memory. And you have a bunch of pages in disk. And suppose at one point I bring this guy over, and that's this person here. That's in my buffer. Okay? And then I have a thread that updates this page. So that, for the most part, it looks like this, but this particular region becomes this. All the other is stayed as before. But this particular small region becomes like that. Do you follow me? Yes or no? Now, if you compare this versus this, there is a difference. There is a difference. And you may argue, what's the big deal? Isn't the case that we mark this as dirty when we made this change? We mark this page as dirty so that this will go back to update this, and this become this as well. One thing, if you recall the discussion we had on buffer manager, one thing we kind of being blurred about is when the dirty page is written back to disk. Can someone answer me that question? When a dirty page is pushed back to disk?
At unpin.
At unpin, yeah. Okay, then let me ask you, when is a dirty page unpinned? So at unpin, you push back a dirty page to the disk? You sure about that? So, yes, you said no.
When
No, the person behind you. Go ahead. Okay. You just decrement the pin count, okay? When is the dirty page pushed back to disk? When the reference count is 0. Well, that's same as unpin, but with a further constraint, the pin count has decrement to 0. Well, not really.
Would it only get written if it's dirty and its pin count is 0 and it needs to get moved out of the buffer?
All you need to claim is that when it is being replaced, because the condition for being replaced is pin count 0. So you don't have to specify addition for being replaced and asking because that's part of it. That's part of the requirement. So the dirty page only gets written back to disk when this page is to be replaced. But then the question is, when exactly this page is going to be replaced? Well, that depends on your buffer replacement policy, depending on what policy you are running. Whether it's RRU or MRU or whatever, I don't know. But when it is the turn decided by the buffer replacement policy to replace this page, only at that time, this dirty page is written back to disk. No matter how you run your buffer replacement policy, one thing that's clear is that if I call this time T1, meaning that the time I update this page as buffer, and I call this time T2, to the time I push back to the disk, one observation I have is what? T2 minus T1 is what? It is not going to be 0 all the time. There is a discrepancy between these two time instances in most cases. Okay? So T2 minus T1 equals 0 with very low probability. Or another way to say the same thing is I'll simply WHP. Okay, WHP means with high probability. Okay? Do you follow me? And what's the problem with that? Well, there's a huge problem, right? So we typically expect somewhere between T2 and T1, let's say from this region, what do you expect to see? You expect to see the content of this page in the buffer like this, and the content of this page on disk like this. And what's wrong with that? The problem is system may crash during this time period. If system does not crash, this is okay, because if you request this page again, I will serve this page from buffer. I don't even go back and check this. You still get the latest view of this page. But if system does crash, what happens? You know what? This is gone. Forget it. No matter how much you love this, you want to keep this, it's gone. Right? You forget about it. Forget about it. It's gone. Okay? Nothing you can do about it. And when you back online, you say, okay, I'm finally back online. Let me re-exploit my knowledge about the database. You know what? The content of this page become this. And this is not going to be okay. This is not going to be okay, right? Because can I demonstrate this somehow? Let me try to do this demo here. Okay, so let me set. Oh, okay, true. Let me start a transaction. Okay. I start transaction, and what happened now? I'm gonna insert okay? And I got my SuperDB in the database. And what happened now is I'm gonna root. And what I'm gonna do is I'm gonna kill this database. Kill it. While this guy is still happily doing his work. I can just do that. Okay? I restarted my database. What happened here? Well, we're still here. So SQL is really. See what's the difference? Do you see the difference? Yes or no? The 107 record mysteriously has disappeared. So MySQL, this code, this database has become pretty good, right? Even if I restart the server, it actually does not kick out the user session. It maintains your session somehow. However, it's not automatic because whatever you can do, the buffer is gone. Right? When you restart the database server, it's kind of like system crash, and buffer is gone. So I still have to print out that you can check. So it automatically recognizes you, but the change you have made is gone. You follow me? Let's do the same experiment. Okay? Oh, this is auto commit. Of course, this is gonna survive. So let me start transaction. Insert this. Now what happens? I check it. Well, okay, it's there, but more important, I'm gonna what? Let me commit. Okay? Now on this side, I'm gonna this evil guy come back and restart this. But you know what? I don't care because I have committed, and the change is supposed to be there. Resilience to system failure. Okay? Resilience to system failure. Okay? You know, if you understand all the discussion so far clearly, if you see everything precisely, close your eye, you think about this, you say, okay, this is trivial, right? All I need to do is what? Is to make sure, all I need to do is to get rid of this and make sure what? Make sure T2 equals T1. Then I don't care about system failure anymore because the change I made is permanent. You follow me? Can one of you tell me what's wrong with that? What's wrong with doing that? What is wrong with doing that?
You're increasing your IOs.
You're increasing your IOs. For example, you bring the buffer back online. So the first time I change this to this, but later on I change my mind. I say, okay, I don't want to change this to this. I want to change this to this and that. In the traditional buffer manager case, most likely, by the time you do the second change, I haven't written this dirty page back to disk yet. So at the end of the day, I do only one IO. Using this new model, this becomes this first, then this and that. 2 IOs. Furthermore, don't forget rollback. You still have rollback to worry about, right? If you set this 2 times to be the same, the rollback becomes a lot more expensive. I may have done a number of statements, then I decide to roll back. If you have this case, rollback becomes simple. You simply what? Throw away these pages from buffer. Throw them away. Meaning that throw away that means what? Set dirty bit back to false. You don't even have to throw them away from buffer. All you need to do is set dirty bit to false. Even though there are some changes already, but you simply change dirty bit to false. Make sure that it's not written back to disk. Of course, you also need to make sure no other transaction can actually read the content of this page. So after all, you may have to still throw away this from the buffer. Okay, but never mind. Throwing away the content of this page from buffer is trivial. Because there's no I/O involved. But if you do this model, rollback becomes really expensive because every change is permanent on this immediately, and you need to go back and change those. And that's not trivial. Okay, so to be more precise, what we mean by resilience to system failure, transaction guarantee all or nothing execution in a system, in a database management system, regardless of what kind of failures you have. All or nothing means that the entire transaction is atomic. Either all the statements in the transaction gets executed, or none of it get executed. You never have a partial state in transaction. I'll show you. Start transaction. Okay. That's basically this goes with this, right? Now, so ignore that. That's fine. So the state of the database is like this. I will insert So what do you expect to see? You will see 3 more records, and the title of that course 514 become from manpower utilization to test. Right? I made a bunch of updates. Do you follow me? I may even do this. So I delete the city planning class. It's gone. Okay? I made many changes. But when you have a system crash, what do you expect to happen? Well, you know what? All or nothing means that none of the changes you have made, no matter millions of zillions of changes you have made, doesn't matter. None of it is supposed to be reflected in your database. All or nothing. Let's try that. Oh, everything is back to normal. 15 back, the city planning class is back, and the 3 new records are gone. All or nothing, all or nothing. But once you commit, what happens? All these changes stay. You're not going to have partial execution of your transaction. Okay. So solution to both concurrency and failures is what we call transaction, which I have demonstrated to you throughout this lecture, right? And transaction is a sequence of one or more single operations treated as a single unit. One keyword you might want to add here is an atomic unit. Atomic in the sense that's similar to the semaphore concept we talked about. Right? Semaphore is a signal control system in a train station. Right? That's what we call semaphore. And transaction appear to run in isolation. I hope I have convinced you that, meaning that one transaction does not see the change of another transaction until the other transaction has committed. So each transaction runs in quote-unquote isolation. It appears that from the user's perspective, is it looks like I have the control of the database to myself. I don't have to worry about the effect made by the other transactions.
Feifei,
Yeah.
before we were looking at concurrency issues where, for example, you have two different users trying to write, let's say, an increment to the same variable. Right? One's 1,000, one's 1,500. And it seems like we're treating the semantics of that such that they both should be applied to them, right? How, is this like an application level? So if we want to prevent, so, okay, so say I notice a bug, I'm a user, I notice a bug in the database, or in the data, and I'm like, oh, I'll go fix it. And somebody else goes and does the same thing, at the same time. How do you, is this like an application level thing?
Very good question. So this is something we're going to discuss in the next few slides actually. There's something called isolation level. And one example of isolation level is called serializable isolation level. And serializable means that no matter how many transactions you have in your system, the end effect, when you finish executing all these transactions, you can interleave actions as you want, but you need to guarantee one thing, you being the database management system. If I ask you to run in serializable isolation level, at the end of the day, you need to guarantee that the end effect of your database is the same as if you were executing them in sequential. One critical observation though is it does not specify what is the sequential order you're using. Because if you have two transactions, it could be T1 then T2 or T2 then T1. Three transactions is even more complex because it's essentially the possible sequential execution of them equal to the permutation of the three transactions. T1, T2, T3, T1, T2, T3, T2, or T3, T1, T2. You know, many possibilities. Serializable only asks you being the database management system, to ensure that at the end of the day, the end effect of the database is equal to the serial one order of the serial execution of those transactions. Doesn't matter which one. So that's what we call serializable isolation level. Then we have other weaker isolation levels. Weaker isolation level means that you're gonna allow more interleaving action of these transactions. So you will see some inconsistency states, some of those inconsistency issues we have discussed. But you know exactly what type of inconsistency you're gonna see at a particular weaker isolation level. One example of that is repeatable rate isolation level. All of this I'm gonna discuss in a minute. But to answer your question, the users of the database management system allow the user to control this isolation level or the level of inconsistency you have by setting a proper isolation level in your database. And in most commercial database systems, there are 4 popular isolation levels. Start from serializable to repeatable rate to those other 2 are less common because they're much weaker than the 2 we're going to talk about. And they will allow many inconsistency to exist. Okay? All right. So we talk about commit and auto commit, so we can ignore that. So to give you, so immediately I'm going to talk about, I just answered this question, but we're going to talk about serializable, right? So imagine you have many users running different transactions at the same time. The default isolation level in a lot of database management system is called serializable isolation level. Serializable isolation level. So you're going to have T1, T2, T10, T8, T9. And you want to make sure at the end of the day, when you finish, when all said and done, when dust has settled, every single dust has settled, the end effect of the database is equivalent to a serial execution of these transactions. Could be either T1, T2, T10, T8, T9, or T2, T1, T8, T9, T10. So any serial execution of this transaction will be okay if you are in the serializable isolation level. Okay? Going back to the earlier example on updating the emission numbers, one statement tried to increase by 1,000, the other tried to increase by 1,500. If we enclose both statements in 2 separate transactions, what is the right serializable? What is the valid execution of those statements if you are in serializable isolation level? Well, either you update the emission number by 1,000 first, then by 1,500, or you can update by 1,500 first, then 1,000. Meaning T1 or T2, then or T2, then T1. Both are okay. Of course, you may wonder, in that particular case, the order doesn't really matter. Whether you do T1, T2, or T1, T2, or T2, T1, the end effect is you increase emission number by 2,500. But in some other cases, T1 and T2, or T2 then T1, actually give you different states of the database system in the end. Well, that's okay, because these two transactions are running in concurrency. In a real world, you don't really know whose effect gonna survive first, whose effect gonna survive in the end. But I do know that in a real world, if you were to execute this in a serial manner, it's either T2 or T1 or T1 and T2. Does that answer your question? Okay. But the point is, a naive solution to give you serializable isolation level, a naive solution is what? Is to allow no interleaving action from these transactions. Meaning that I fix the order. Let's say I tell you it's T2 then T1. Then what do? You execute T2, then you execute T1. But that's very inefficient, because T2 might have one operation. For example, I read a bunch of nodes. I decide to compute a TSP on top of it. And this TSP computation may take 2 hours. And if you decide to go with T2 then T1, what you're saying is, read this node, compute TSP for 2 hours, then execute T1. And T1 may be doing something like read a bunch of nodes and calculate TSP. And the right thing to do is what? Is to run this TSP calculation in parallel, so that you cut the execution cost by a factor of 2. Rather than executing T2 entirely, then T1. So a critical observation is, you do allow actions from different transactions to be interleaved, as long as interleaving those actions leads to an end state that's equivalent to a sequential execution of those transactions. As long as that's guaranteed, I don't care how you interleave those actions. Of course, you may choose not to interleave any action at all, and that obviously guarantees serializable isolation level. But typically, database management systems do not do that, because that's very inefficient. I think I have to stop right here. If you have a question, we can take this offline.
So my question basically is still, what if only 2 users doing that, and one updates like 1,500 and one updates like 1,000? Say only one of those should be logically, it makes sense to only apply one of those transactions.
Why? If both transactions commit, then both changes should be reflected in the database.
From the database's perspective, or maybe from the business perspective.
From business perspective, if you allow the other user to be the administrator of the database, you have to leave with the consequence that the other user might update this value. If you don't want to see any other person to update the database, well, you know what? Revoke the access of the other user to the database. That's not the responsibility of the database system. It's really the way you run your business. Make sense? But if you do allow another user to have administrator access to the database, well, you have to be prepared to the fact that while you are making changes to the database, the other user might make change as well at the same time. Might be making changes at the same time. And the database system, what database system guarantee you is that I will give you a serializable execution of those transactions.
So you need to write your code differently.
You need what?
Write your code differently to run something.
Well, you don't have to write your code differently. It's just that when you reason about the behavior of your database, you need to be aware of somebody else might make changes to your database. Okay, all right, that's all for today. Happy Thanksgiving.